intervals of time. The classic experiment let's back this up. A measurement of interval of time, or fundamental way to measure interval of time, is with a light clock. A light clock is simply a photon is beamed up to one end, and there's a mirror in this end, and the light bounces back, and it defines an interval of time. An interval of time would be described as the distance divided by the velocity. Okay, that's fairly straightforward. And then now at some time in the future, or if this was in the past, well anyways, at some time later in time, if we have a photon go up and now go from one end of the time to the other end of the mirror to the other, it would define a longer interval time. And it'd be a longer interval time not just because of the distance, but because the velocity of the photon is actually diminished. The speed of light is not constant in this model. It is constant locally, but not when viewed from an absolute perspective. Now, when we look at the interval of time defined, and we do a ratio to compare the two, we see that the intervals of time will vary to the absolute ratio of time. So in the past, let's say we're 1/2 the age of the universe, it would take 1/2 the amount of time to define that interval of time. A fairly straightforward relationship. But would this be true for everything? Would all relative measures of time maintain this same proportional relationship? And let's go over here. Let's look at, for example, an object with angular momentum. And we have, at one time, it takes a certain amount of time to complete one rotation at t1. Here we have at t2. And if we do the same, the interval of time defined by this relationship, we end up with the same interval. The change in intervals of time is equal to, or geometrically being defined actually by, the ratio of time. It would have been, if this was 1 second here, it would take 2 seconds here if the age of the universe were to have doubled. So in this case, it is maintaining a proportional relationship. In fact, what's being established is conservation of angular and linear momentum if the object was simply moving from point A to point B with a certain velocity. Now let's take a look at something a little bit more complicated. We have a pendulum this time. And how is its interval of time changed? Well, the period of a pendulum is 2 pi times the length divided by the accelerative field that the object is experiencing to the square root power. So if we include how the measures of distance and acceleration change, and we were to apply it, we would see that the change in time is again inversely proportional to the ratio of time. Clocks are keeping their proportional relationship. Let's take another look at another one. This is actually Kepler's third law, where the period squared is geometrically proportional to a linear measure called the semi-major axis cubed. Okay, and if we go through the relationships again, we see that the interval of time is geometrically inversely determined by the absolute ratio of time. So all clock rates are maintaining their proportional relationship over time. If it took 1 second to occur, they're maintaining a proportional relationship over time. A kind of structure is being imposed. Now, let's see if we apply it to some other relationships, such as forces, like F equals ma. Dimensionally, force equals ma has mass times units of distance divided by time squared. If we make the substitution of the ratios of time for how distance measures change, and we substitute how the intervals of time change, we would get that the force, or what would be the accelerative field, would vary to the t to the 4/3 power, which is exactly what would happen when we took the first derivative of the velocity. The second derivative of the distance measures how it changed. We are getting exactly the same rate at which accelerative fields are to vary. So it is consistently producing not only the acceleration of how the points in an expanding space-time object would change, but also the behavior or the accelerative field that would be experienced by that object. Okay, and is maintaining this 4/3 relationship. And you can do it in a couple different methods, and whether it's gravity or F equals ma, you will still get the same basic relationship. Here I did it with centrifugal force over here, and then okay, but in essence what's being, I call the inverse square laws, are being established as a kind of structure of space-time. Now, I do it over here with work, force times distance, and again we get the same kind of basic relationship. And I would do it with potential energy, where, let's say, the energy of an object is going to vary when we go through the relationship to the t the inverse 2/3 power of time. And then if we do it, for example, with nuclear energy, equals E equals mc squared, we see that a relationship again varies exactly to the same measure of time, that the energy of an object is going to vary to the t to the 2/3 power of time. Whether it's kinetic energy or nuclear energy or the intrinsic energy of a mass at rest, they maintain this kind of, so the fundamental relationships of nature are being predicted by the proposed assumptions of the model. It's forming, everything is conforming to a kind of geometry. Now there is a problem when it comes to the energy of a photon, and the energy of a photon is proportional over time to the frequency over time, the speed of light over time, or the wavelength over time. So if we look at it from the frequency alone, which would be the based on the proportional intervals of time, we can see that it measures inversely linearly, which is not to the 2/3 power of which energy of objects, like intrinsic rest energy of a mass, is not changing at the same rate. And if we just, as another check, use the this relationship where the energy is proportional to the speed of light divided by the wavelength of the object, we get exactly the same relationship. So the inverse varies inversely the ratio of time. So we can see we maintain the relationship is consistent within itself, but it is not maintaining the consistency or the constancy of the relationship of measures of distance and time, measures of energy. So there's an issue. This is one of the problems that I had with the initial present model, that matter and energy weren't maintaining their equivalency. And so far, as it presented in this phase of development, where it's just considering the expansion of observable space, there is no equivalency between matter and energy. They are not keeping their equivalency over time. And this talks about a cosmological redshift issue. Now, there's also an issue with respect to the cosmological redshift. If in the past the electrostatic field around an atom was greater, there would the energy imparted to the photon would be greater and the wavelength would be shorter. Similarly, if it loses energy over time, it's going to have that energy diminished, and the relationship doesn't work out right. We end up with a confusing or ambiguous relationship with respect to the cosmological redshift. So that's another problem for the model. Now, some people may ask, well, what about special relativity? Or general relativity? Doesn't it destroy all the relationships of that? Well, the most fundamental relationship in special relativity has to do with what's called the Lorentz factor, or gamma. And here we see this is represented, the gamma is equal to 1 divided by the square root of the following term. 1 minus, and then in parentheses, the velocity of the object divided by the speed of light of the object squared. Well, this ratio, velocity over c, these both change at the same proportional rate. So gamma does not change. It maintains its proportional relationship over time. So it is not being affected. Also, since relative measures of distance and relative measures of time are maintaining their proportional relationship within time, they are also keeping their proposed relationship with the passage of time. Now, I should mention now, since clock rates would be faster in the past, that would mean that the total amount of time is different. It would be greater. If the tick of the pendulum was faster in the past, then the cumulative measure of all those ticks would be greater than what would be assumed if we just look back in time. So we have an absolute, what I call a cosmological or historical measure of time, which is the eye of God perspective, and then we have a cumulative measure of time. And here we have how relative interval, let's say we establish this is an interval of time here, and if we go to, for example, when the universe was 1/5 its present age, clock rates would have been 5 times faster. Now, if we want to get the total, the cumulative time elapsed, we would take the integral of the relationship, and we get the total cumulative measure of time. We end up where it's a natural logarithmic function based on a ratio of time times the age of the universe. They get kind of straightforward if those familiar with integral calculus. We get that relationship. And now over here, what we have is an interesting comparison where I plotted the amount of time that's actually elapsed. And we have, if this is the age of the universe assumed in the present, we would see that for objects ticking at the beginning of time, an almost infinite amount of time would have elapsed from the beginning of time to where we are now. Now, this is only using the model based on expansion of observable space. This relationship will have to be amended or properly described only until the relationships of unobserved space are included in these relationships. And I'm going to stop here, and then I'll continue on with measurements of how measurements change in space. Stop.